In this lesson, you're going to customize and tune the Flower project you built in Lesson 2. You will learn about many aspects of federated systems that you may often want to tune, and you'll implement a custom training schedule in this lesson. Alright, let's dive in. Compared to traditional centralized training, federated learning introduces some additional concepts, some additional components in the training process that can be customized and tuned. One important factor is how do you select the clients that participate in each round. In this diagram, you see 5 clients. So instead of sending the global model to all 5 clients, you could send the model to just 3 clients in the first round. The 3 clients would participate as usual. Then, in the next round, you could select 3 other clients. In a setting where there are only a few clients, the answer is often just select all clients in each round. If you have just 5 clients, as in this diagram, you would probably select all of them in each round of federated learning. But then, in settings where you have large numbers of clients, you would typically not do this. In fact, it has been shown that selecting more and more clients has diminishing returns. What you would do instead is you would select just a subset of available clients. In a mobile setting with millions of clients, you would often just select a few hundred clients in any single round, or at most a few thousand. Depending on the task, there are different strategies for selecting those clients. A very common one is to just select them randomly. There are also approaches that are, strictly speaking, not federated learning, but that can be very useful. One example is cyclic training, where you would send the model to one client, have that client train it, send it back to the server, and then send it to the next client. And you would do that for one client after another. Another factor is client configuration. Once you selected clients, you need to decide how to configure them. What do you want the client to do? How long should it train the model? What hyperparameters should it use? Are there any other things the client needs to know to execute the training or evaluate in the right way? You can see the small model icons on the client highlighted. This is to indicate the client configuration that the client uses to execute the task. A third example for something that is commonly customized or tuned is aggregation. In federated learning, there are very different approaches for aggregating model parameters. You've seen and used federated averaging in the previous lesson. There are many other approaches like Q-fed averaging or fed-adam that provide certain improvements over vanilla federated averaging. The Flower framework you used in the previous lesson has many of them built in as so-called strategies. Let's jump into the lab to see how the server can configure client-side training. As usual, you start with some imports. In lesson 1 and 2, you manually partitioned MNIST to simulate multiple datasets distributed across multiple user devices or multiple organizations. Instead of manually partitioning data among the participants, you can use a library called Flower Datasets. Flower Datasets provides us with a class called Federated Dataset. This abstraction will partition many existing datasets like MNIST, and it allows you to generate small training and test sets for each client. The load data function loads and prepares the data for federated learning. It takes a partition ID as input, which specifies the partition of the dataset to load. The dataset used here is MNIST, and it is partitioned into 10 partitions. The loaded partition is then split into training and testing subsets with an 80:20 ratio. This is done using the train, test, split function. A custom transformation is applied to normalize the data. Data loaders are created for the training and testing subsets respectively using a PyTorch data loader. Along with model parameters, you often want to send configuration values to clients. Configuration values can be used for various purposes. Let's say you want the server to control the number of local epochs performed by each client, so the number of times the local client iterates over the local dataset during training. To do that, you define a function called fit_config that takes only one argument, the current server round, and it returns a configuration dictionary. In the config dict, you put a key called local_epochs with an integer value that tells the client how many local epochs to train for. In this example, you can see how you can vary that number depending on the current server round. Here, we sent 2 in the first 2 rounds and then 5 for round 3 and later. The client can use this value to dynamically change the number of local epochs it trains on the local dataset. It means that the client will train for 2 epochs initially and then increase the number of local epochs during later rounds. Next, we initialize the federated averaging strategy as usual. We set fraction evaluate to 0 as we don't intend to perform any client-side evaluation. And we pass initial model parameters to the strategy. Now, to make the strategy use our new fit_config function, we simply pass it to fed averaging during initialization using the parameter onFitConfig_fn. Passing an onFitConfig function to federated averaging will make the federated averaging strategy call this function every single round. The returned config dict will be included in the message that is sent to each client. It calls the function every time to enable you to send different configuration values to the client every single round. Last, we define an instance of server app. You also create the Flower client class as usual. The only difference is that you want to use the local _epochs value from the config dict. The fit method in Flower client class is responsible for training. It takes 2 main arguments: parameters, the model parameters from the server, and config, the configuration parameters for training. As usual, the method begins by setting the parameters of the model using the provided parameters from the server. The number of local epochs, local_epochs, is extracted from the config dictionary to determine the number of epochs for local training. Here, you log this value and then call the train_model function. The train_model function is called to train the model using the client's local training data. This is stored in self.trainLoader. This time we pass the number of local epochs as an additional argument. We then create the client function and client app as usual. Let's run server app and client app and see what happens. You can see that the Flower server app starts and it performs 3 rounds of federated learning. It initializes the global parameters that are provided by the strategy, and then it proceeds to the first round of federated learning. The strategy samples 5 clients out of 5 available clients, so it samples all of the available clients, and then it sends the config dictionary along with the model parameters to all the participating clients, so to all of our 5 clients. You can see that the first client logs that it trains for 2 epochs, so does the second one, and so do all the other ones. After the training finishes, the aggregation function receives 5 results and 0 failures. You can also see that there's a log that says no client selected, skipping evaluation. This is because earlier on, when initializing the federated averaging strategy, we set fraction_evaluate to 0. So no evaluation is performed on the client side. In round 2, we see pretty much the same thing. We can see that all of our clients, all of our 5 clients are selected, and you can see that each of those clients trains for 2 epochs. Now, looking at round 3, you can see that again 5 clients out of 5 are selected, but then you can see that suddenly the clients, instead of training for just 2 epochs, they're training for 5 epochs. And this is caused by the configuration dictionary that those clients are receiving from the server. So the number of local epochs is controlled by the server, and the clients react to whatever configuration value they receive from the server, and they perform the appropriate number of local epochs. The configuration dictionary is a pretty flexible concept. You can put many different kinds of keys and values in that dictionary, and it's a perfect thing to experiment with. You could experiment with different hyperparameter schedules, for example. You can use it to send the learning rate from the server to the clients and control the learning rate that each client is supposed to use. And you can use it to control many different aspects of the client-side training process. Feel free to play with this and experiment and let us know how it goes. Let's review lesson 3. Federated learning introduces additional hyperparameters. It introduces additional concepts that are important to control the training process. On the server side, we can customize and tune things like client selection, client configuration, and result aggregation. On the client side, we can configure things like the pre-processing, the local training, and any kind of post-processing we want to do on the weights before sending them back to the server. A flower strategy allows you to customize all of those things that we talked about on the client side. It allows you to customize client selection, client configuration, result aggregation, and server-side evaluation.